this is the last talk of our fun conference, and our last speaker is Simone Cecchini, and he got his master's degree under Paolo Piazza from University Roma Sapienza. And then he moved to graduate school in Northeastern University, where he got his PhD under Maxim Braverman, who actually spoke here a couple of times. And after having postdoc in Germany, he's now at Texas A&M University.
Yeah. Okay. Yes. So, thanks for the nice introduction, and thanks for the invitation. So, okay. So today we're gonna talk about metric inequalities with scalar curvature. So let me first fix what is my handwriting. Very reasonable.
Yeah.
Don't
Don't ask that.
So we start with the Riemann manifold M, and well, the scalar curvature is a scalar values function, not surprisingly, from M1, and well, as any curvature, of course, it encodes information about the shape of the manifold near each point, and the value of the point P is going to be the 1 minus P over N. Oh, now the start is over 6. Okay, R squared plus okay, so what's written here basically is that it tells information about the
On the left, you have the volume, right? The volume of a ball.
Oh my God! Yes. Sorry.
Okay.
No. This is
Yeah.
This is the volume of the geodesic ball over. Yeah. Sorry. Over the volume of the ball of same radius of the space. Otherwise, doesn't make any sense. And so this means that in particular, so we are interested in positive scalar curvature, and this means exactly that if you take a very small ball and the manifold of positive scalar curvature, then the volume of the geodesic ball is going to be smaller than the volume of the ball with the same radius in the Euclidean space. Of course, this is true for R very small, and the prototypical example is going to be the N sphere. N sphere, which has scalar curvature. Maybe denote it in this way. It's going to be N times L. And okay, so since I want to talk about metric inequalities, I mean the main point is that the scalar curvature has so the existence of metrics of positive scalar curvature on a manifold actually imposes conditions on the topology of the manifold. So this is the main point. And so maybe let me there are two main techniques to study metrics of positive scalar curvature that are. And maybe I should also mention that the reason why we focus on positive scalar curvature is that every manifold of dimensional history always has a metric of negative scalar curvature. So in other words, there are no topological constraints whatsoever. So there are two main techniques. One is the minimal average surface. Minimal average surface. And the second one is the Dirac operator. Now the minimal average surface is start with Schoen and Yao, so end of the 70s, and the Dirac operator technique. I mean, this actually goes back to Horowitz, and the topics that I'm discussing today are more related to the work ground fellows. So today I will mostly focus on their operators. Maybe I want to make one more observation so both techniques have restrictions. So the near surface technique has a dimensional restriction. So it works up to dimension 7. This has been lifted to dimension 8 in the 90s, and it has been extended to dimension 10.
Yeah.
Very recent, actually. Something like 2 months ago. This is a very nice result. I want to mention this is by Mantoulidis and Chodesh and Schulz. I hope I spelled that. On the other hand, Dirac operator technique, I mean, works in every dimension, but it requires the manifold to be spin. So, I mean, spin means, let's say, more than length. Means that you can refine even further okay. Anyway, I will explain later. Now, I'm always nervous when I start talking. So the first thing I want to point out is what is maybe the most important metric inequality when it comes to scalar curvature. And the most important one is comparison with the sphere. And here, so this is a result, this theorem due to Leroux. This is from, I think, 96, even if, I mean, it's quite recent actually. I mean, in the sense, all this work is end of the 70s, beginning of the 80s. Well, the theorem is the following. So take M to be a closed spin manifold, and suppose that F is a map with the round sphere. So G0 is just the standard round metric, and suppose that well, first of all, that the degree of the map is not 0, and second, suppose that F is area non-decreasing. Now, this is a metric condition, this is a topological condition. And all right, so now if
when you say non-decreasing in volumes or something, is that what you mean by that? Areas, okay.
So it means literally that it doesn't increase the area of surfaces.
Of any surface.
Yeah, that's right.
Oh, okay.
I mean, actually, so you can think of it as a generalization of being one Lipschitz. And then what happens is that either there exists a point such that the scalar curvature at P is smaller than n times n minus 1, which is the scalar curvature of the sphere, or F is an isometry. So this is, so the picture here is clear that you have a manifold M, okay, it's closed, so it's and I have a map into the round sphere, and so in other words, what's written here, I mean, this has two parts, right? So one part is that basically it's so the part that we will discuss today is that if the Riemann manifold dominates the round sphere in the sense of scalar curvature, so that you have degree non-zero and non-decreasing, then it's never possible that the scalar curvature dominates the scalar curvature. So this is an obstruction result. But on top of this, there is a rigidity result that is more difficult to prove, and I will not discuss it. Now, just to mention that this result of Yerur is actually is a let's say a sharp version of a method that was developed by Gromov-Flausen. So in other words, using Gromov-Flausen, you know that there must exist some constant such that if those two conditions satisfied, then the scalar curvature cannot be bigger than this constant. However, the idea of Yerur was to, well, was to pick the right bundles, and I will discuss in a minute because I want to explain the idea of the proof, to really estimate this constant. And this constant turns out to be exactly the scalar curvature. Now, to discuss this theorem, you see that here there is a spin assumption. And the reason is that this theorem is proved using Dirac operator. And then to explain this theorem, I will discuss quickly, the basic, let's say, the basic ideas of the Dirac method. So, Dirac method. So, here you start with a manifold. Now you need to assume that the manifold is spin. Now this is a topological assumption, as I was saying. This means exactly that the structure group of the tangent bundle can be refined to the dimension 3 to the universal cover of S1, which is. So now, if a manifold is spin, then you can construct on M, well, a Dirac operator. So what is a Dirac operator? And basically is the square of a Laplace operator. And so, in other words, you can use the spin structure of M to construct a bundle S, a bundle with connection, and an operator going from smooth section of this bundle to smooth section. And now this has two main properties. So the property number one is that this actually captures, is related to the geometry of the manifold, and in particular to the scalar curvature. And this is the Schrödinger Mitchell square. So saying that the square of the Dirac operator is equal to nabla plus 1/4 times the scalar curvature. So nabla is the connection. I mean, this is a bundle with connection over. Okay. Now, so this is this tells you exactly that. Now, this is of course a non-negative operator, and this tells you, in other words, that well, this tells you that if you know that there exists a non-trivial harmonic spin, or some solution of the differential equation square u equals 0, then you cannot have positive scalar curvature like this. Now the question is how do you solve PDs on manifolds? This is extremely difficult. There are many ways to do this. To do that, one very classical way when you deal with Dirac operators is using indexing. And then in particular, assume that M is closed, then and even dimensional. I mean, so this assumption can be dropped by using more refined index theory, but today I will just consider index. Now, if this is true, then the bundle S is going to be C2 graded, and in particular, the kernel the plus, which would be the Dirac operator restricted to the positive bundle, and the kernel of the minus are going to be finite dimensional, and in particular, the difference is what is called the index, B. And by ideasing the index formula, this is a topological invariant, and it can be computed just out of cohomological data. So in other words, this is the integral over M of a certain, differential form, and this is topological invariant called the head genus. Okay. And maybe number 3. So what is the easiest example where this works? Is the Cecchini surface. So if you take n to be a Cecchini surface, then n is going to be spin, and the heterogeneous is in 0, which shows that Cecchini surfaces have no PSA. Now, to deal with this case, you need a slightly modified version of this. So in other words, I can take same data, I add one more bundle, and then I can twist the Dirac operator and make it act on sections of S10 and of course the Schrödinger formula gets modified accordingly. So here you have one more term where this is a endomorphism of S10 to S, or a zero-order operator whose norm is after constant. So after constant is the norm of the curvature of the connection on E. Okay, and now if you look at this formula, this also means that this is going to be greatly equal than. Well, okay, even if we forget about the inequality, if you look at this, this actually dictates balance. Okay, so in other words, if you know that you have positive curvature, then what you know is that if the index is non-zero, and then you can construct an unvanishing section here, then this cannot be too large. And okay, so then sorry, the other way around, then the scalar curvature cannot dominate this stuff. Right. And okay, so now if you write and then the index of this is going to be again modified accordingly. So here you can add these decorations, and this becomes, well, a certain commutative formula. So this is the checkout of E, and then again you have this plus, and okay, so this is again a TSC limit. Now you go back here. Then the idea is the following: take a sphere, and then I can take on the sphere the spinor bundle itself, and use it as a twisted bundle. The advantage of this is that the index is going to be just the other characteristic. I mean, this is characteristic plus, and then I can construct the operator E twisted with, I can pull it back to F. Now, since this depends on the curvature depends on two forms, and therefore when I pull it back, that's the reason why it's enough to assume area monochronism. And then I can consider, in other words, this bundle over this manifold N. And now this bundle and twist the Dirac operator. And now if you write down the Schrödinger formula for this operator, knowing that you have a non-vanishing spinor coming from the computation of the index over the sphere, then you also know that the scalar curvature can never be bigger than what actually. Now you have to compute this term, but this is just the spinor bundle over the sphere, and then this norm is going to be exactly in terms of. So that's the point, that the connection that you put here is the Levi-Shaped connection you can compute it. And this, of course, takes care, let's say, of the obstruction part. Okay, the rigidity, I'm not going to discuss it. Now, a second, so in other words, so this is the main comparison theorem with positive scalar curvature. So the moral of the story is exactly like a closed manifold can never dominate the sphere in this sense. Of course, so what are manifolds that do not carry positive scalar curvature metrics? Well, the main example is, of course, the torus. Yes, but why? And then again, this follows from this theory. Actually, this was proved way before, because it was proved by Gromov-Pelosi. But Gromov-Pelosi and Shane-Yama independent. Now, the theorem of Gromov-Pelosi is that well, the torus has no AC. Okay. So why it follows from this? Because you take a torus, right? So just look at it as a hypercube, and now take larger and larger covers. And this means that you can construct maps that are more and more contracted into the one sphere. Here is the map. And this means that on the other end, the scalar curvature is completely local. So if you lift it, it doesn't change. And then if you know that you have a positive scalar curvature on the torus, you can take a cover that is large enough, take a map that is contracting enough. And then, of course, all these formulas get rescaled, right? And then at some point, you get a contribution. And maybe I want to mention that this is true for the torus, and it's true also for, well, the torus connected with actually any, well, maybe let me call it Y, with any spin manifold, and moreover here, you can also take a product. So you have a large class. And maybe a comment is that if you use mean upper surface method, the big theorem, no one knows at the moment how to drop the spin assumption. So the reason is that the mean upper surface method requires many homology classes, and well, you have a sphere. So good luck with that.
But the N has to be a manifold that doesn't admit a positive scalar curvature metric, right?
Oh, this N, sorry.
Yeah.
This N is something that has non-zero index.
Right.
Yeah,
Okay.
Let's say with non-zero, I had genus,
Okay.
of course.
Yeah.
Otherwise, of course, it's not true. Okay, so those are the basic. So this is the basic comparison theorem, and this is pretty much the main obstruction result. Then you can refine it a lot, but this is the basic version. Now, if you don't cross it with N, this can be proved using Mueller surface. And the reason is that, well, the torus is exactly the prototypical example where Shane-Yama works. However, for the K3 surface, it's not clear how to use Mueller. This is another question. At the moment, at least no one knows. Okay, but today I want to discuss manifolds that are not closed. Okay, and so what's the point? Take manifold with boundary, and then now, so take X to be a manifold with boundary. Now, on a manifold boundary of dimension 3, on an open manifold, actually, dimension 3, you always have a metric of positive, sectional curvature. So this is a result of Gromov from the 60s, which means that on a manifold with boundary, you always have a metric of uniformly positive sectional curvature, and therefore scalar curvature. And this means that so if you have a non-empty boundary, you cannot have any topological obstructions. So metrics of positive scalar curvature exist all the time. You can take it, of course, as big as you want, and so there is no obstruction whatsoever. Then you want to put extra geometric conditions. I mean, a typical example is take a torus crossed with a segment. I'll take something like this. And now suppose that the mean curvature is greater than 0. I mean, when greater than 0, so in my convention means that it's opening up. Then, for example, take this example and then suppose that the scalar curvature is positive. Then you can double it. This is a result. I get a Gromov solution, and then you get a contribution. So this is an example. So today I want to consider some different metric conditions, and this following actually questions of Gromov from this topic. So let me. I want to keep. Okay. The question Gromov. So the question number 1 is the Loganek problem. So this is actually a quantitative version of Euro. So in this case, you assume to a map, okay, blah blah blah. Let's make the same assumption, but with manifold boundary. So in other words, take a manifold and now as an empty boundary. Here is some topology. And now suppose that you are mapped into the round sphere. And well, the assumption is actually that you're gonna that this map is gonna send the a certain neighborhood of the boundary into a point. Okay. Then the degrees are defined. You assume that degrees of 0 and f is area of degrees. So same assumptions to make sense of it. I mean, you need some room, otherwise you cannot. And then now the conjecture is that if the scalar curvature, so now let's call this x g. Now, if the scalar curvature is greater or equal than a certain positive constant sigma, this is over, and moreover, plus all this assumption, okay, then well, and moreover assume that the distance between the support is map called f, support of the differential in the boundary of x is greater or equal than Cn. So the conjecture is that it exists a constant depending on n, such that if those two conditions are satisfied, then the degree of f must be 0.
And there's no restriction on the boundary, like with the mean curvature or anything?
No.
Okay.
I mean, there is, I will explain it.
Okay.
Indeed, in the end, it turns out that there is.
Good.
So this now, let me put it here, that shows the degree of the 0. Well, now this is, so this actually is, I mean, this is solved actually. It's a theorem now by myself. And so the point is that you can get a precise estimate. So in other words, so suppose that so in other words, if the scalar curvature of G is greater or equal than sigma, and the degree of f is 0, and and f is area from increasing, and if you ever get anything, then the distance between the support of the differential of f and the boundary of x is more equal than well, I have to read it. Well, is actually should be high. Oh, sorry. But I proved it. Okay, it's high. Okay, actually. So the point is that I usually don't include sigma. I just consider enter 0 as 1.
Yeah.
Yeah. But this is the general formula. So this is this is the first result. So this is a quantitative version of the obstruction result here. So as you see, this is a very concrete constant, which is nice. So it's not like there exists something you can estimate.
Okay.
Wow. And these are I will explain how to do it as well. But maybe let me. I want to get a big picture of this. So then, so there is a conjecture number two. So this is again due to growth. This is about similar situation, but now, so you see that basically what I do here, I consider sort of the case when the topological information actually is contained in some open subset, so something of full measure. Okay, but now you can make a different point. So take something that does not have scalar curvature, for example, torus, and then take a product. You just cross it with a segment, and now ask whether this maybe one observation. Sorry, not observation. One important point is that this has to be spin. Otherwise, this really cannot be proved. Your new observation just doesn't work.
Also, with your theorem.
Yeah, without spin assumption.
Okay.
At the moment. So now, so start with and maybe one more observation that I want to make is that the fact that so we're using, let's say, classical technique, you can for sure say that if I take, let's say, attach an infinite cylinder or actually any element, it doesn't matter. Let's say, compact, I can never put a complete matrix of uniform velocity approach. So the idea is the following: if I know that I cannot do this. So in other words, if I for sure I can put, let's say, metric of uniform velocity by curvature, I don't know, up to here, okay, with a certain way. And suppose that you try to push it. This actually is obstructed. So this was already known. So in other words, at some point the geometry must collapse. You cannot keep going. So the main point actually of this theorem is that the point at which the main point collapses depends only on the lower bound of the scalar curvature and the dimension of the link. So does not depend on the geometry. So that's the main point. And actually, with the torus now, take something like this, you can make similar reasoning. So take a torus, I can take, so this is N. Of course, I can always put same reasoning, metric uniform deposit scalar curvature on a compact cylinder. But however, I know that I cannot put a metric of uniform deposit scalar curvature on an infinite cylinder, which is complete. I mean, a metric deposit curvature which is complete and which has a polynomial uniform bound, which means that basically here you will have a similar situation. So the geometry must collapse. And then the question is whether you can tell where, at which point this happens. And the answer is, again, this was conjecture, but from more in general. So take Y to be closed manifold with no PSC. So now no PSC is more general than any non-vanishing index of whatever kind. So there are counterexamples. I mean, I know that some of you are, like index theory, and of course you can consider way more general abstractions. And for example, you twist with I mean, you can take the Michel Crofomerico bundle. You get the most general non-obstruction to the existence of PSC. It is a flat bundle with infinite dimensional fiber. However, there are still examples where this index is 0. However, you cannot have. So it is just known that this for simply connected. However, the index characterizes the existence of PSC matrix P manifolds by results of Stefan Stolz. But in general, this condition is way stronger. And plus here we're not making spin assumptions, but just to say that even if you restrict to spin, this is anyway. So if you take Y to be a post manifold, which does not carry on the scalar curvature, and then suppose that take Y crossed with I, put a metric on it. So this is what Gromov calls a Riemannian band. I mean, actually, the notion is more general than this, but this is enough. So, and then suppose that the scalar curvature is greater or equal than some positive constant, then the width, so let me call it V, then the width of V must be smaller or equal than exactly twice that. So I n minus 1. See. All right, so this conjecture actually came before this one, and of course this number is strongly inspired by it. Yes.
Is mentioned on the Y prime side usual product method or
I will explain it here. So that of course the product metric cannot have PSC.
Yeah.
However, and this was exactly the example that we're down now. The work product metric over the flat torus can have positive curvature, and this is exactly the comment that I want to make right now. So where you see that there I said okay, there is a constant and so on and so forth. So where does this constant come from? And the constant comes exactly from the fact that if you take over the torus, or actually anything which, but anyway, or the torus, take the metric. Now I have to read the constant. To read the working function. This, but there is a power, and then I want to get it right. Yes. So sorry. It's G over 2 minus 2. Okay, times G0 plus B squared. I mean, it's constant. I mean, it's clear that. And now here you can show exactly that this has scalar curvature equals to n times n minus 1, and the width is going to be exactly 2 pi n. Oh, let me think. N times n minus 1, 2 pi over n. Yeah, just basic. Okay, so then the diagram was exactly that. Okay, this must represent some, for bands, this must play the same role as a sphere that was made. So this was the basic. Now this conjecture is maybe a remark or a position. This is Gromov again. This is I think 16. I mean, indeed, this holds. So the conjecture holds for the torus, for y. And this is done with minimal of the surface. And now, of course, so what can you do with the Dirac method? Well, you can prove this conjecture with exactly this bound, but now you replace the torus with whatever as an index abstraction. So what you can say, this is a theorem, is by myself and my collaborator, Simone. So what you can say here is that actually, suppose that you have actually any index abstraction to TC on the core. So in other words, for example, if y, let's take the case of n times the torus with a genus of n different from 0. Just to say general. And then the conclusion holds. So in other words, it's the scalar curvature, then conjecture holds. So the point is you get then you can generalize. So all these questions. I mean, there are many other versions, but maybe the thing that I want to point out here is that so this object is really supposed to be rigid, right? So you expect a theorem like yellow, and indeed, actually, this is true. This is again due to myself and Sadler. So we prove rigidity with a small extra assumption on the mean curvature. So now I'm not going to write. So there are a lot of constants, and for sure I'm gonna but the main idea is the following. I think if you explain the idea, it's better rather than give you heavy formulas that I don't even remember. So, so the idea is the following. That now you see why I started to talk about manifolds boundary. So now take so put a metric over here, and suppose now that you have that you have a map into the entorus. Let's suppose that we stick with the entorus, then you can generalize it. So the main point is the following: that if I know the width, so in other words, of course, if I take the width smaller than this number, for sure I can have I can arrange a scalar curvature graph. However, what I cannot do is to put a metric which has exactly scalar curvature equals to n times -1. That has width equals to, let's say, this width. Okay, this is some number smaller than pi, and such that the mean curvature is smaller than the mean curvature here. I mean, the intuition is clear that the mean curvature tells you that the manifold is close enough, right? And of course, the mean curvature. So what happens when you approach the this number is that the manifold collapses, meaning that the mean curvature is going to -1. And now what happens here is that, okay, if I take this,
You're taking that outward mean curvature or the inward mean curvature?
okay, with respect to the inward, meaning that if you
Normal.
push out, and so okay, so mean convex, so positive mean curvature. Let's fix meaning that if this is the boundary and I am inside the manifold and I push aside, this is going to open up. So this means positive. Okay,
so that would be the inward.
That would be the inward.
Inward normal. Okay.
So I guess let's say anyway. So we agree. Okay. So the mean curvature of the boundary of the ball is positive. So this is what the convention. So here you have rigidity, which is something that you didn't have. So you also have rigidity, which is nice enough, I think. Plus, maybe I want to point out that, okay, 15 minutes, maybe I can do. Yeah, maybe I will give you the big picture, then if you want details, I will give details, of course. But I think it's because now this work actually started more than 2 years ago. Now it's all clear, I think. So so maybe I want to make this so to over the big picture now, let's formulate one more conjecture. Okay, so to see so what happens with bands. Bands are way better understood. The problem is that for bands we have model spaces. Okay, for this, not clear. So you can prove that the bounds are sharp, but you don't have model spaces. So you can sort of by approximation you can do it, but you don't have model spaces, no rigid. And this maybe making mention if someone is interested in this topic. So this is related to what's called geometric relativity. So the positive mass and this kind of thing. So and even there, okay. So for the ones who know a little bit of this topic, rigidity there is really difficult. So maybe not surprising that the rigidity here is very complicated. So. And now the conjecture number 3. This is due to Rosenberg and Grom again. This is take M, take Y to be a closed manifold of dimension greater than equal to 5. Dimension, maybe let me call it, a dimension M-1. Then the following, so Y has no, let's see, then that this is the best you can do with bands. Okay, so in other words, let's call it band curvature bound. Almost. And then number 3, there are no complete PSC metrics on Y cross R. So this is, let's say, strong, and this is also. Okay, this I think we discussed. However, there is one point that, as I said, there is a big discrepancy between what you can detect with index theory and the existence of matrix of this coverage. But for simply connected. So if the manifold is simply connected, then there is a theorem by Stefan Stolz saying that for the dimension of this 5, the existence of PSC matrix is completely characterized by the non-vanishing of an index that is a little bit more complicated than we have to work with real system, real before. And so in other words, to go so this so the equivalence of 1 and 2 for simply connected manifolds follows from this theorem. I mean, from the more complicated versions. However, index theory is not, it's not constructive. So to go, if you drop if you consider in the general case, index theory doesn't give you a way to start with the PSC metric here and construct a PSC metric on the slice. Minimal per surface can do that. And indeed, so in other words, the equivalence of 1 and 2 is proved well. For simply connected, again, spin follows from that theorem. So actually for all simply connected, actually it's true, and this is true up to dimension. So let's say 1 in equivalence is true for up to dimension 10, and now we're using this new results, and simply connected, or simply connected, but with no dimensional restriction, but simply connected. And now one can ask, what can you say about point 3? Point 3 is not covered by this band, because here we're assuming the existence of a uniform uniform bound for the scale function. But of course, here I'm just assuming complete PSC. So meaning that we can consider an infinite cylinder and a scalar curvature that is positive by the case. Okay. And so can we rule out something like this? Now the answer is again yes, using next. So this actually is something that's been done by many authors. I did a very general version. I mean, this is known due to results of, for example, Bunke, for example, Angel. Bunke. And then okay, since again there is some similarities between the Dirac methods and the minimal surface, actually the way you perturb it, that I most likely will not discuss. Then recently, actually, together with again, this is from last year. This is from last year. 22. This is to okay myself, but why most people outside the and now when I give talks, I'm very nervous. Ready? Okay. So we also use minimal per surface actually, so not direct operators, to prove that 2 is equivalent. And here the interesting part of this is that actually I have 5 minutes, maybe I will quickly tell you how to do it. But now this is all clear. So this is the big picture, and I think this is quite clear. But maybe so what's the technique actually here? So the technique is to use potentials to modify the Dirac operator. I mean, basically, you have 2 methods, as I was saying, that is the minimal per surface and the Dirac method. Those 2 methods actually, the clear relationship is no one knows, of course. It's complicated. However, you can use potentials to perturb these techniques, and then you get exactly the same quantitative bounds. So that's the interesting part of the stuff. And then this is exactly the idea that we use to do this. So for example, for a band, you can take just you take the Dirac bundle over the band, and then you can just take S plus S, and then you're going to take the operator. I write it in a very simple-minded way. You can, if you consider an operator like this, then the main point is that the square of this operator is going to be greater or equal than psi squared minus psi plus the scalar curvature over here. And this means that if the scalar curvature is positive, I mean, this becomes, you can solve it. And the solution is going to be exactly, it's going to be this. That's the, I mean, so in other words, well, it's going to be this if the scalar curvature is exactly in terms of the form.
I'm confused about the dimensions. In the conjecture, is the n-1 greater than or equal to 5?
Yeah, that's correct. Ah, yes. So
You put less than.
oh,
Yeah, okay.
sorry.
Now I understand.
No,
Okay,
it's
thank
really
you.
different.
Yeah, okay.
No, I mean,
Yeah, okay.
in dimension 4 is not true. Actually, it's enough to different from. But anyway, so
Okay, okay.
I mean, in lower dimension, you can do it by. I mean, up to dimension 3, everything is classified, and everything is spin. Then, if you take something like this is going to be spin as well, and moreover, in dimension 2 and 3, every manifold that does not carry positive scalar curvature also has a vibration. This is not true in general, but in low dimension.
Yeah, and one equivalent to 2, is that now known for all dimensions or no? Or no?
This is not known for them.
Okay, okay.
This is
Okay.
this is known, let's say,
It's just
as long as the mu upper surface method.
Sure.
And by the way, the mu upper surface method, that there are these new results that make you think that really maybe it will take time. But look, there are no, at least this is my opinion. I don't know, but it looks like there are no conceptual issues. So in other words, let's say it's not proved. This is not proved full generality, but if they will, as I hope actually. So if they can generalize the neural surface method, I already mentioned that. All this stuff. Oh yeah, so this is definitely building. And so the idea is here is that you see that you can take the Dirac operator, solve this equation, the solution gives you a function that is exactly the it's going to be exactly the mean curvature. So it's not this much. It's going to be exactly the mean curvature. And this means that that basically, if you well, this means that if it is longer than that bound, then this function blows up. If I find time, and then so I know that suppose that the band is bigger, and then I know that I have a function that goes up. Then I can hit the brake here, make it then complete, but of course here I can take a constant that is big enough to control any term that I want. So the point is that this equation gives you a shield. Okay. So in other words, you know exactly that you cannot go more than this width. Now, if the width is smaller, then the point is that the solution of this gives you exactly the mean curvature of the standard of the model space. And now the mean curvature from the point of view of Dirac operator with boundary conditions, this gives you exactly the boundary term. So the boundary term is going to be psi, so in other words, minus, well, actually after constant, there is an m-2 constant that I'm not considering, minus the mean curvature. And therefore, you know that if the mean curvature is smaller, then you get something that is positive, and this gives you contribution. So it's basically nature of its method plus potential. You can do it on a band. So this is, let's say, passive index theory, and you can do it in that case. So as a matter of fact, from a geometric point of view, what you need to work out something like this. It's two boundaries that are is one. Here, you do it in this way, and then the topological information is completely contained in actually any slice. In this case, the topological information, yeah, since the boundary is pulled back from the sphere, and you know that this is going to be central point, this means that the boundary is trivial near the boundary. Then now you can take a second trivial bundle, and then consider the two boundaries, the pair of boundaries, let's say, call E the pullback of this pair of boundary. Then your pair bundle will be just the pullback of E with pullback connection, and the second bundle would be just the trivial bundle connection. And now you can use the isomorphism between those two bundles that exist only here to construct your progression. You make it start from 0, and then well, how much room do you need for the differential equation? Half the room, and then you get exactly this constant. Okay. So I think that's all I wanted to say. Yeah. At the beginning, I was very nervous, but anyway, so